Okay, so I'll explain in the framework of multiple scattering theory how we do the calculate impurity, and we extend that to how do we calculate the situation where we have impurity doesn't have to be single side, it can be multiple sides. So how do we solve the impurity problem? It turns out to be a very convenient in a multiple scattering theory. So so first of all, let me explain a multiple scattering theory approach. So it's also known as KKR method or Green's function method that we all know here. And the first of all, what happened is we divide space into non-overlapping domains. And so there's no gap between domains. And each domain we call atomic cell. Each of the cell contains an atom. Right? So based on the location of atom, we basically just construct like a big cell for each atom. Of course, you can make it more complicated by not putting a plane in between, just right in the middle, in between two atoms. Can be, depending on the atomic size, you can make a proportionally, you can move that dividing plane. It did happen that one time I did this niobium hydride calculation. I found you have to give niobium more space. Hydrogen atom have less space, so sometimes you don't want to put a plane in between. So you might want to move around. But anyway, so the whole point is you try to divide the whole space into atomic cells. Then the LDA or GGA potential in the whole space is essentially just divide into in between all the domains, so that the potential itself is a collection of non-overlapping atomic scattering potentials. So that is you have an effective potential in the entire space, but in between, inside each given cell, the potential is the effective potential. But this Vn is a local potential, means that it's zero outside. Okay, so we're not changing the potential itself, but rather we define the local potentials. So the local potential only is the LDA or GGA potential in the cell, but outside is zero. So that's kind of local potential. So consider such a local potential as a single side scattering center. Okay. Then the crystal wave function, it turns out, is just the standing wave solution of this multiple scattering problem. The reason called multiple scattering because we have many scattering centers around in the space. So this condition will be it can be applied to solve the band structure problems. On the other hand, in the scattering theory, you can construct so-called Green's function for the Kung-Chen equation corresponding to this effective potential. And that is, so for each given atomic cell, you can calculate the T matrix for this given potential. Remember, this potential is defined inside this domain and is zero outside. So this kind of a local potential. You can calculate T matrix for it. So I'm not going to talk about how T matrix is calculated, but just remember that you can calculate scattering matrix corresponding to the potential. I'll find some other time to discuss how this is done. And then if the potential itself happens to be spherical, okay, if like you make a muffin approximation that you ignore the shape of the cell, but rather you make the potential to be spherical. So that is, you can define an inscribed sphere inside this cell, and you let the potential to be zero outside the sphere, and then assuming that potential to be spherical. In that case, you have such a potential has a very clear definition for the partial phase shift. And that's the one we learned in quantum mechanics. In quantum mechanics textbook, the potential is all spherical symmetrical. All right, it's easy. It's textbook problem. So you can calculate this phase shift delta sub L, and that delta sub L is directly related to T matrix. Okay, but anyway, so in general, we have to deal with T matrix, but there's no way you can define phase shift anymore because potential is non-spherical. So the point is, in general case, we don't deal with the phase shift anymore. We just only deal with scattering T matrix. Okay. So for the Green's function is expressed this way. We can talk about some other time how this derived, but this is the exact expression. Okay. For single side problem, if the whole space only has like a one single atom with this local, then you can calculate the T matrix for it. The Green's function for that single problem is the tau is replaced by T. Okay. In general, you have a collection of scattering centers. So tau represents the multiple scattering problem. Okay. Z is the single site. That is, you're asking yourself, what is the Green's function in this domain? So this is how it is calculated. That the Z is and the J are single site solutions for this single site, this particular potential. That is, this potential is 0 outside the cell and it's non-zero inside the cell. And this is a single site problem. You can calculate the single site solution corresponding to the potential. Okay, Z and J correspond to regular and irregular solutions.
So this this tau is the same as T matrix?
No. Tau is a multiple scattering matrix. T is a single scattering matrix.
Okay.
If the space has only one single scattering center, that is, if there's only one atom in the space, this tau will be T.
Yeah.
Okay. But now in the crystal, you have scattering centers all over the place, right? So you deal with tau. Okay. So the Green's function we're calculating here is the Green's function for in this domain, given the fact that the whole space has scatterings all around all the in the entire space. Okay. But even though you have a scattering all over the place, but now your question is, what is Green's function in this area, in this region? So what I do is I just construct Green's function this way. This is the exact solution. This is the exact solution for the Kongshan equation. Okay. So tau represents the multiple scattering effect, while Z and J are regular and irregular solution for a single site problem. Okay. The crystal effect is built in this tau. Okay. Another thing I want to mention that the block wave solution happen to be the poles of this tau matrix. Okay. Okay. This L, obviously tau is a matrix. The matrix index is L. L is little l and m. We know quantum mechanics. Little l is the angular momentum quantum number. M is the magnetic quantum number. Okay, that's just it's all written in atomic physics. So this is basically what this is all about. So having Green's function, we can calculate charge density. Okay, the whole Kongshan equation. The goal is to find this rho, right? That's what we want. So you can either solve it by solving the wave function, or you calculate by taking this Green's function. Either approach will work. But this whole theory is exact. It's comparing to like a pseudo potential approach or FRPW like Vin2K. The Vin2K is an approximation. So this KKR method is only one and only exact solution for Kongshan equation. Okay. So it's essentially an exact method. It's an all electron, so it's not a pseudo potential. But anyway, so all right. From the theoretical point of view, of course, numerically you have to implement all different numerical techniques, but from the theoretical point of view, it's the only exact method. Okay. All right. So I'll mention how the tau is calculated before I can go further to explain the impurities problem. Okay. So by definition, the tau matrix represents the multiple scattering process for electrons starting from site N, then being propagated to site M. Okay, so this N and M means starting from atom N and end up in atom M. Okay, but of course there are many different scattering processes. This first term represents it happens to be M and N as the same, so you have to keep the first term. Otherwise, the first term will not be there, right? So this term means that scattering from side N to M, right? So this is a propagator in between. This says that the third term says that it's starting from N and go to K and go to M. Okay, this is another scattering route. All the other terms scattering many times and end up at M. So basically, it's a scattering, describe a scattering process starting from atom N, end up at atom M. Okay, so this is tau N, M. The definition of tau M is. So you can write this down as like this. Where G is a Fourier transform propagator, and it's also called a real space strut constant matrix. We can spend some other time in the future and I'll explain exactly how this GNM is calculated. But anyway, so you can write that into this form. You can figure it out by yourself easily. You can have this iterative expression. Okay. Of course, you can. That's one way of calculating tau NM, but this is not very effective way to calculate it, tau NM, by this iterative method. Another way is you can move it around to find out this kind of matrix approach. Okay, you can define this called an M matrix by putting this T inverse in between. This the result which is coming from here. You can work that out by yourself, and then you put a minus G at the off diagonal corners. Okay. And tau M end up is you take the inverse of this matrix and take an NM block. That's what you get. Okay. So this is a little bit more convenient to do. If you happen to have a finite number of scattering centers in the space, this is how you can calculate tau M. This is how LSMS is calculated. LSMS calculating the tau is ways you have a cluster in the vacuum, right? You construct M matrix this way and take inverse, take an NM block. That's how we calculate tau NM in LSMS. So there's a special case. If the system is periodic, that is all the T is the same, then you can do by what you do is you can still come back to this expression and insert this e to the k dot r into this expression. This is series, and you can work out yourself. End up you have this expression that you can define this G to be a Fourier transform of this k Latin Fourier transform of this real space strut constant matrix. End up you can have this expression. Okay, this is derived from this iterative expression. You can derive by yourself, but we can, I just give you the result. So that is, if your system has periodicity, that is, you can calculate the tau matrix using this formula. It's much more convenient. Given that if space has filled up the infinite number of scattering centers, right? But it's periodic. So this is a more convenient approach to calculate tau NM. Okay. So this approach is, if the number of scattering centers is finite, so it's convenient to use this method. But if it's an infinite number of scattering centers, happen to be periodic, so this is a more convenient approach to calculate tau NM. But the whole goal is to calculate tau NN, so that we can calculate Green's function in this. Okay, that's our goal, right? But so this is kind of background knowledge why tau is important quantity to calculate, because we want to calculate Green's function. Okay, the whole major computational work in multiple scattering theory approach, no matter KKR or LSMS, is all trying to calculate tau NNs, so that will calculate Green's function. Okay, that's all. That's the whole work is built up around it. Okay, now let's talk about impurity now. Well, given that fact, okay, so if you have a unique atom surrounded by all the other atoms to be the same, so we have such a problem, right? So how do we deal with how do we do the calculate tau for around if this is the atom N, how do we calculate tau N? Okay, if the impurity, that is, we calculate tau matrix for this impurity. The reason called tau matrix because this is given that all the surrounding atoms is a tau host atom. Right? So how do we calculate tau matrix? All right, we use this definition. We use this way of constructing that. Of course, assume that there's an infinite large number of crystals, but this matrix could be infinitely large because the number of atoms in the large. I use this matrix form I can only use the matrix form because the other special case is a periodic case, but it's not periodic anymore. So I just use this form to construct the so-called M matrix. So remember, for M matrix, only one atom is the impurity atom. All the other atoms are host atoms and get to be the same. And there's all the off-diagonal are the this stretch constant matrix. I'll put it as that. So that's kind of what I've done in the previous slide, show you how to calculate tau matrix, right? So first of all, construct this M matrix. And then what I do is look at this picture. So this embedding case, this impurity in the surrounded by host atom can be break into two pieces. One piece is everybody is a host atom plus the impurity atom minus the host. What that means in terms of M matrix is I'm doing the following things. Okay, I'm not breaking the algebra. It's the same thing. You add these two terms together, you recover this M matrix, right? So this picture reflects the fact that I break the M matrix into two pieces. One is that the first matrix is the host system, that all the atoms are the host atoms. Okay. The second piece is a T matrix, the difference between the impurity and the host atom, and everything is 0. Okay. Then I take the inverse of it. I take a 1-1 block. That's what tau matrix is, right? A 1-1 block because the number this is atom 1. Okay, this impurity. So I take 1-1 block, and then this whole thing is this matrix. Okay, H means the host. I have double column means that it's a block matrix. That means each element is a matrix, but it's a block matrix. So the whole thing is so I have double column represent that. This expression means this guy. Okay, it's a block matrix, but since only upper left corner is a non-zero, it's Ti minus Ti inverse minus Th inverse, and then I take the whole thing inverse, take 1-1 block. That's what the tau 1. That's the tau 1-1 that is. That's what I want to calculate. Then you can take just linear algebra now. You take a M matrix out of this expression. Okay. Now, next thing, it becomes this. Of course, it's not very obvious how you get from here to here. But if you want, you can work that out. But I think I'm going to work out for you how I get from here to here. Okay. But anyway, so I'll explain that in the next slide. But so that this tau 1, that's what we want to calculate Green's function for around this impurity. That I needed this tau 1. So what I do is tau 1 atom 1 is the impurity atom. Is M matrix inverse, take 1-1 block. Okay. So that's a kind of conclusion from here. Of course, I'm going to show you how I get from here to here. All right. And by the way, tau host is the tau matrix for the M matrix inverse. That's the whole thing is this the host atoms. It's a periodic system. Okay, for pure crystal, right? The tau, as I showed you before, the tau matrix can be calculated using the case-based integration technique. I explained that previous slide, right? So that's how I calculated. So this is just kind of case-based approach to calculate tau matrix. Okay, so this explains tau matrix is calculated using this case-based integration technique. And then all you have to do is multiply tau to the difference between Ti inverse and the T host atoms inverse. And plus 1, I take inverse and multiply to tau host. That's how we calculate tau matrix for impurity. Okay. Now, I'm going to explain how do I get from here to here in this expression. All right. It's not quite straightforward, but let me give you a little show you how it happens. First of all, this is the host M matrix. What I'm going to do is, because it's 1-1 block is the tau matrix, right? M matrix inverse. The 1-1 block is tau matrix. I'm going to put it here. It's tau matrix. And I can put everything else as a kind of matrix block. I don't care what they are, but I just say called A12, A21, A22. Okay. And A22 could be a square matrix, but A12 and A21 doesn't have to be square matrix. Okay, because size of A22 could be larger than, of course, is larger than tall H. Okay, but anyway, so I just break that into like this block, 4 blocks. Okay, so given that, remember I'm gonna take a look what this really is. Okay, that's the kind of expression I got from a previous slide, and then I'm gonna write into this kind of block forms. So 1, 1, and this I'm just gonna take this expression, put it here, and remember this guy is that I have upper left corner is a Ti inverse minus T host inverse, and everything else is 0. Okay, I put it here, and this guy I'm just copy that down from here, all right? And my goal is take the 1, 1 block to calculate the tau matrix for the impurity side. Okay. Now you can just you work that out, taking this matrix multiplication and plus 1, 1. That's what you get. Okay, you can easily figure that out, and that's just kind of matrix multiplication and plus identity matrix. That's what you get. Okay, remember there's an inverse here. Okay. Now, how do I do that? I just apply this simple formula. A, B, this inverse, this whole matrix block, this another matrix block, this identity matrix here, there's a 0 here. You take the inverse of it, it turns out the result is this. Okay, so you just apply this formula to do this inverse. This is what you get. Okay. Okay. Now, because I'm only interested in the final result, I'm only interested in this 1, 1 block. Okay. So what you get is easily, it's 1, 1 block. So you can easily do the matrix multiplication. That's what you get. So that's the formula I'm getting. This here shows how I get this tau matrix for the impurity. Okay, this is the kind of result I get. This is not kind of any ad hoc or some assumption. This is exact expression. Okay, this is how we do impurity calculations in the framework of multiple scattering theory. All right. All right. Okay, so that's how we get this KKI CPA works. Is in the CPA formalism that we have like impurity particular given chemical species surrounded by a CPA medium, and then we take a single side approximation. That is the average of this tau alpha means that this alpha could be different chemical species, right, from 1 to n alphas. So you take the C alpha is the content of the given chemical species. Your average of this guy, tau 1 sub alpha, is the tau matrix for this particular chemical species. The average over that's supposed to give you the CPA, tau CPA. So this is a single impurity problem. Okay, the tau alpha 1, 1. That's what we have just derived. But for this time, for CPA problem, the host atom is just CPA medium. Okay, and that's why I put CPA instead of H there. And for periodic system, because this is a CPA is a periodic lattice, and on each side is a TCPA. That's why I calculate the tau CPA this way. Okay, so this is entirely how the KKI CPA works. And the critical part is this impurity problem is solved using this expression, and the tau host this CPA tau for CPA is calculated using this formula, because the whole system is periodic. And TCPA is turned out, because we don't know what TCPA is, that's what the goal is, to find the TCPA. So we just solve it iteratively. Okay. So once we have tau alpha, so we calculate the Green's function for it. We are able to calculate Z and J because given particular alpha, it's a known atom. We know potential for that. We can calculate Z and J for it because we know the potential. We calculate regular and irregular solutions, and can construct the Green's function for that given chemical species that give you the Green's function. And then you calculate charge density for that. Okay, so this is how KKI CPA works. and how impurity calculation is done in the framework of KKR-CPA, in the framework of multiple scattering. All right, so you can certainly extend that single size to double impurities. Okay, you break that into like this. You do exact same way. The M matrix now is a cluster, so you have two. You break that into two pieces. So you have this whole thing. This matrix is this host system. All right, everybody the same. See the on diagonal, everybody the same. So this type of calculation, the total matrix for this kind of system can be calculated using case-based method. And of course, you have two impurities. Then you have this matrix have like a upper left corner is two blocks, which are T1 and T2, corresponding to T1 and T2. All right, two different atoms. And then you can do exact the same approach, except now you got this guy is just this guy. All right, this M host is this one. So you can just do exact same algebra, and you take the linear algebra, take the MH out, and make it become inverse. You can prove, okay, exact same process I showed you for the single site. Now they have two sides. You get same thing, get this result. Except now, the difference is, tau hosts have double column, double line, double underlines. Means that this is really it's not single atoms case anymore. It's a two atoms, so actually have a little block. I'll explain to you later on. But so then take one block, you can calculate this tau. You calculate tau matrix for this site. You can calculate if it's a tau CC22 that's this site. Okay, I take 1,1 as an example here. So that's the tau C11. It's a C means cluster, but have double impurity. So that's the tau matrix for this guy. Okay. By the way, so this expression tau TC inverse, my TH inverse now is a two block matrix now, 2 by 2 matrix block. And a tau host, and this guy here is a 2 by 2 block. Okay, so it's kind of extension to the single impurity case. But now you have the matrix size a little bit is bigger, twice as bigger, because you have two impurities. Okay, these expressions are exact. All right, so how about embedding a cluster? I have a cluster of atoms. Do this break, look like this. It's the same thing. This tau C11, you try to calculate tau matrix for this guy, you take the 1,1 block. If you want to calculate tau matrix for this guy, you take 2 block. If this is number 2, if this is number 3. If you want to calculate tau matrix for this guy, you can get the CC33 block. But depending on how your numbering is, depending on how you put the T matrix in the location of T matrix in the whole M matrix. So you have 1, 2, 3, the total number of atoms in the cluster. So I take this atom, central atom as number 1 as an example. Okay, 1,1 block give you this. Yes. Question?
No.
Okay. Okay. All right. So exact same construction. So end up this is the result. Okay. So this guy end up now is such a big block matrix. The size of the block is the number of atoms in the cluster. And the tau host, NC is the number of atoms in the cluster. And tau host is this guy. Now it's a block matrix. The reason it has to be this one because really you have to deal with is a fact that it's a cluster. It's multiple atoms in the cluster. So you have to deal with how do you calculate tau 1, tau 1, 2, tau 1, NC, and tau 2, whatever, all these things. But remember, this is a system for the entire for periodic system. But you still have to calculate tau 1, tau 1, 2, tau 2, 2, all these things. These quantities. So how to calculate it? It turns out, we call the expression for the previous one of the previous slides. If your periodic systems have tau, everybody's the same. So you calculate tau nm is using this formula, right? I've shown this in one of those older previous slides. This is how we calculate tau m. Okay, now, so therefore we have for the host atom, if say you just apply this formula, that's what we can calculate. Okay, tau m is calculated this way. So use this tau m to construct this this block matrix, which the size is of the matrix is size is corresponding to the number of atoms in the cluster. Okay, so this is the whole approach how we take to calculate embedding in the framework of multiple scattering theory. So down the road, we're going to do LIZ embedding that will have a cluster of atoms embedded in the effective medium. Effective medium could be a typical medium, right? So we'll still have to work out how that typical medium is calculated. But no matter if we can calculate effective medium, we'll have to find out what the TC is. How to find the T matrix for that effective medium. That's how we can calculate tau matrix for that, and then we can calculate Green's function. Okay, so I think that's what I want to say about for this. Explains how the impurity and even cluster embedding is calculated in the framework of multiple scattering. Any questions? Really, Kami, I want to hear sometime in the future how you do impurity calculations.
Well, the impurity we usually talk about is different from your impurity because we're talking about explicitly dealing with the interaction in the impurity. So, so your impurity problem is still a scattering problem. It's still a non-interacting problem.
Okay.
Except the constant potential.
Yes.
So when we do DCA or DMFT, when they call about impurity problem, the impurity problem is a site with explicit interactions term. Understand what I mean? So your system is like, okay, I get impurity. Basically, I take one of the atom out of the system, for example.
Mm-hmm.
Right? But that atom is represented by a potential.